Okay, let's get started, and let me briefly recap what we've been doing so far. So last time was we talked about optimizations and gave you some examples and the mathematical model, the mathematical models for optimizations. And there are several categories, but in these lectures, we want to focus on convex optimizations. I show you what's the definition of convex functions and the definition of convex set. And once we figure out that the optimization problem belongs to convex optimization, one of the biggest advantages that here it's all local solutions are global solutions. So you don't have to worry about whether this is local minimums or global minimums. So it's a good advantage of having convex optimization problems. And another reason is that many problems that we're going to face in the machine learning turns out to be convex optimization problems. I'm going to show you those lot of examples in the regression problems and the classification problems as we go on this lecture. And once we're done with the modeling of convex optimizations, the second step I mentioned is that how to find the optimal solutions. There are two ways. The first thing is take the derivative or gradient when you have multivariate optimization problems. And the second thing actually that I want to emphasize is using the computer, which is iterative method. And one of the example of iterative method that I show you guys is the gradient descent method. So it's very intuitive. Since we don't know optimal solutions, start with the random initial points and compute the gradient and give us the output, give us the directions for the next update of decision variable. And there are something we have to see. There is some step size, which is running rate. What if we have large value of alphas? What if we have a smaller value of alphas? Or what kind of situation that we're going to have? And how do you, here probably is the smarter way is adaptive, which is we might want to reduce the size of the value of step size alpha as we go the iterations. And the convergence problems, we have that, and we don't know whether it's a local minimum, that's global minimums. In that case, in practical way, it does not guarantee, but it turns out very the effective is that start with random initial points and try them multiple times to get. So this is the kind of practical way to overcome for non-convex optimization problems. And I think that's where we stopped. And let's continue on. So this one is, the first one is get the exact solutions if we have close the mathematical expressions for optimized objective functions. And another way is gradient descent, which is iterative method. For the benefit of gradient descent, it's easy to implement, as you can see, and it's very general and it's applied to any differentiable. But here is loss function is same. You can think of same as objective functions. So any differentiable, the objective functions you can apply. You can apply gradient descent methods. That's why it's very general approaches. And it requires less memory and computations. This one is probably not easy at this moment for stochastic method, but later on, probably once you have a chance to do the user gradient descent, probably like in the homework assignment, probably you can recognize it. So gradient descent provides general learning framework. And that's why we're gonna use for classifications and regression as well, and like artificial neural net. And here, I mean, I haven't mentioned what's the neural net or artificial neural net or deep learnings yet, but when you trained the neural net models from the data set, the optimization process is gradient descent. Just have that in your mind. Later on, we're going to revisit. And practically, how do you solve optimization problems? Is the good news is that for many classes of optimization problems, a lot of researchers have already done a lot of work for developing numerical method. So we're gonna take the wide range of tools that can take optimization problems in natural forms and computer solutions. There are many optimization solvers out there, but in these lectures throughout the semester, we're gonna use CVX or CVXPY as an optimization solver. I mean, I think most of them, I'm pretty sure that most of them, this is gonna be the first time that you heard and saw the CVX, right? It's only for the convex problems. As you can see, this is convex. So we have numerical optimization solvers that I'm going to introduce in a minute. So you can download it and you can install it using that with the Python. But from this, in this lectures, we decide to use a Google Colab. So how do you combine the CVXPy or use the CVXPy libraries as modules in the Google Colab? Probably next time, the TA in this TA is gonna demonstrate or show you how to use the CVXPy in Colab in Python environment. So probably next lecture is going, part of the next lecture is going to be the how to TA is going to show you to use the Pythons or Google in Google Colabs with the Pythons with the CVXPy libraries. And for the gradient descent is for neural net or deep learnings. And you might heard the TensorFlow is developed by Google's, and basically what the TensorFlow is, it's optimization solvers most likely use the gradient descent method behind. So this one, in these lectures, we're not going. I mentioned several times that I'm not going to cover deep learning, so you're not going to use a TensorFlow. No, we don't use that. But for graduate students level, we have advanced the AI for mechanical engineers, and in that case, I'm going to cover deep learnings, and we're going to use a TensorFlow a lot. Not for this semester. So summary. There's some. For the general optimization procedures, you start with a random point. We're gonna repeat it. Get the gradient descent directions and choose the step size and update it. And we're going to repeat that process like here until we satisfy the sum of the stopping criteria is satisfied. We can limit it as a like number of iterations, or the increment says it's smaller than some predefined values. Probably you have, that's going to be the stopping criteria. All right, this one I can stop here. I can skip that. And okay, that's most of the theory part that I want to share with you for the optimization. Of course, this is just very brief, the small part of the optimization theory, but I believe that is good enough for machine learning in order to have a better understanding of optimizations for the machine learnings. So I'm going to show you some of the examples that here. And the title is linear programming. The definition of linear programming is that this is a part of optimization problems. The objective functions and the constraints, if those two are both linear, we call it linear programming. And of course, it's convex as well. So you can see that we can utilize the CVXPY later on. So one of the examples is like that. As you can see, this is linear, and say we have two decision variables, in this case x of 1 and x of 2, and we have constraint like given is inequalities. What do you think? How do you solve? I mean, here is the maximization problems, but again, I mentioned the minimization and maximization are pretty much the same. The only difference is I put like here and minus sign on it, so it doesn't matter. So let me ask, how do you solve this problem? How do you solve these optimization problems, or how do you solve this linear programming? Any ideas? X of 1, X of 2, it's the decision variables can have any values within the feasible regime, and with that values, I want to find the X of 1, X of 2, such that maximize these objective functions. All right, and I think the first method here is using the geometric approach. And probably what you can see is that you can do that is you can set as this one is C. Then from that one, like what you can do, like this is a linear equation so like you can draw in two-dimensional space x of 1, x of 2, and this is the slope is -2, and let me see, slope is -2. So probably you might have this. I mean, that's the slope, but C can have any value. So we might have, having different C's, we might have different the straight lines, but the slope should be the same. Right? And since this is the constraint, let me see, let me remove that probably. And this one, let me see, these are the feasible regime. And here, I want to maximize that one, right? By having like, so I'm pretty sure this is very intuitive that I have at this moment going to have the maximum value of C, which is right. So I plug into that values over there, like 2, 3, so it will be 6, maybe like 10 point. That will be the solutions. I mean, I guess you guys already know how to solve that problems. And the second method, actually, this is the purpose that I introduced these problems, because I want to show you or demonstrate how to utilize CVXPY for the convex problems. I mentioned that linear programming is part of the convex problems, so we can use the CVXPY. And same problems, and let's convert it in the standard form so that the CVXPY can recognize it. And again, it's two column, the column vectors, and want to change to minimizations, and here like that's the same as our objective functions, and here and greater than and smaller than. Actually, this is not the mathematically correct, right? But in CVXPY, this means this is got short notations to say that x of 1 is like that, and x of 2 is like that. So let me say it again. This one is mathematically wrong. It's not the correct way to, but I mean, everybody can easily understand. So I use that notations, meaning that each element had some inequalities. All right. Now, how can we program it into so use numpys as an NP and import it, and we have to import it the CVXPY. So we're gonna use short notations with the CVX. Short notation for numpy is NP, and we have to define, here is F is like we have transposed it. So F is like that. And for lower bound and upper bound. Again, I'm not gonna go in details for the what's the meaning of the arrays and what's the meaning of this, and I mean you have to study by yourself, because I mentioned several times at the beginning of these lectures, I'm not going to go over how to program in Python. So if you're not familiar with this, probably you can Google it and search for it and I'm gonna ask you for the self-study for that materials. And we have two unknown variables like here. So CVX dot variables. Remember, we have to use capitalized, so it's variables. And it's this is the shape. It's 2 by 1. And remember, it really depends on version of CVXPY that you're gonna use. And sometimes this is true, or sometimes you have to do it that way. So if you start with anyone and execute it, if you have some errors, probably you can try the other one, right? And I'm not sure which one is gonna use in this semester, but just be aware that there are two. I'm not sure which one is, but try that one and this at the same time. Probably is you guys can figure it out which one is that we're going to use. And the objective functions is like that. Minus, because we're going to have minimize, minus F transpose times X. And again, it's capitalized it. And constraint, we have to define X is greater and equal to lower bound, and X is less than or equal to upper bound. That's the constraint. And what you did is that we have these mathematical expressions for optimization problems, and it's convex and happen to be linear programming. And we up to this point, now we tell the CVXPY, this is the optimization problems that I'm going to ask you to try to solve. And CVX problems, we have objective functions and the constraint and ask to solve. And I want to print out the values. So here, I guess, what was the true solutions for that? Here, let me, what was the 2 and 3, right? So it got almost 2, I got almost 3. Because as you can see, this one is, I guess, use the iterative way. So it's not exactly equal to like 2 and 3, but you can say it is almost same. And the result is, that was the same as the previous, the way that I solved this problem. So, okay, this one is the first demonstrations that how to use a CVXPY for optimization problem. That's the only reason that I introduced it. So later on, whenever you have machine learning problems, I'm going to convert it into optimization problems, hoping that that's the convex problems. If that it turns out, if that's the convex problems, we're gonna use the CVXPY programming like that to find the solutions. That's the general way that I'm going to attack or explain all the machine learning problems. The next example is that starting from the linear programming, and the second is quadratic form. It's the same as the second order polynomial equations in scalar form, but I'm talking about in the vector and the matrix. So in the quadratic form, say X is like column vectors. So we have n-dimensional space. And this one, now I'm hoping that it's inner product. It's the same as I will say like, I hope that all of you at this moment you always get familiar with this the 2 norm squared and inner product and X transpose times X all represent the same thing. Now I want to get here, suppose we have different coefficient like here. Then what we can do is X transpose H. H is a matrix like that. Then like always you have to think about the shape. If you have like this diagonal matrix, then or we can do have like squared. If you have off diagonal terms like here, say I will say then we're gonna have in among them we have so we're going to have this coefficient for the interaction terms as well. So I hope now this is quadratic form. In many case, H is a symmetric, or in many cases it's a semi-positive definite, but again, don't worry about these kind of things. But it's quadratic forms that here we have that. Pretty much in the conceptual wise, it's pretty much the same as the like like this kind of things in polynomial in scalar way. So quadratic programming is that the quadratic functions in objective functions, but here it's a linear inequalities. And I guess that's the decision variables. And this is the form that the CVXPY is required. I mean, this requires to have in order to understand. So all we need is that we have to transform it like that in the quadratic forms, and we have linear forms and inequalities and equalities and lower bound and upper bound. So again, all you need to solve the quadratic programming using the CVXPY is that recognize what H and F, A and B, A equal and B equals, and lower bound and upper bound. How to find the solutions? Don't worry about it. The CVXPY is gonna do that for us. So from this guy, let me, okay, I have to go, let me see, what would be H? Let me, I will compute. Here, this one, I would say, let me try that one. What will be the, I guess, let me see, and zeros. Plus, I would say, is that correct? This is H, this guy is F. What about this? Let me show you that we don't have any equalities. But these are, we do have lower bound. We don't have upper bound, and we don't have equality constraint. Here again, I'm doing this part. And just be cautious on the direction of inequalities. I will say like that. This one, yes, like that. Like this. So let me, with this one in your mind, and F, we're done with the F here, and H over there. A is, this is A matrix, and the B matrix, and lower bound. That's all, you define all the matrix and column vectors, and defined the quadratic programming or convex problems using the CVX, and ask to, I mean, say, define it and ask to solve. And it's the optimal solutions computed by CVX. And one thing that I want to notice here, this one is, that means it's 0, right? Because again, it's a numeric or iterative way, so it's a resolution errors in so it's, I mean, here is, I mean, once you saw that, it's okay to believe that the optimal solution is equal to 0. And for that one, I will say X is 0 and Y is 5. And the value of C is like, is 20. All right. Let's move on to more interesting problem. And suppose we have, I mean, this is the example of finding the shortest distance. Suppose we have this kind of problem, this kind of thing. Think about this. Let's see. Let me think about some kind of the situation that we have. Suppose you are at the concert, and this is some stage here, and singers are standing at these locations to sing, and this is the location that the audience is supposed to sit anywhere around. And we want to know which one is the best seat or locations that I want to sit. Probably here, we don't know yet. And we have to define what's the meaning of the best. Here, suppose that's the shortest distance from the singers to the audience, probably the best. I guess that's the simplest assumption that we can have. And suppose this is the seat that you want to have, but in that case, the coordinate will be like that. So the decision variables that I want to find is that, and I want to minimize the distance. I will say x of 1, x of 2 minus, and that's the distance want to minimize. And x of 1, x of 2, this is the constraint. Should be greater than, and less than this. So this is the constraint that is represented by the equations or inequalities. All right? And this is, in that case, it's two norms, the same as if you take the square, because I don't want to have root, so I want to get rid of these things. The optimal solution does not change. Okay. And we can convert it to these problems, identify which one is H and F and these kind of things, and repeat the same things and go back to use the CVXPY and find the solutions. Let me ask, what will be the optimal solution in this problem? What will be the optimal solution in this problem? I mean, you don't have to compute it. I mean, this is, I said this problem is extremely easy, so we can get the solution intuitively. What will be the minimum distance? Probably I will say like that. So this is the minimum distance that the audience can sit, or you guys can sit. And I guess and let me ask the CVXPY. It turns out pretty much the same. Right? So it's a quadratic program problems, but here the only difference is starting from not starting from the equations. I start from the problems, and the task that you're supposed to do is that you do optimization modeling and use the CVXPY to solve the optimal solutions. Let's try different example like here, empty buckets. And I'm going to show you the situation that we have. And suppose you have, over there is river. And you are standing right there with an empty bucket. And you have to get waters from river and to deliver this location, B. I'm moving from A to B, the shortest distance is probably that way, but in that case, then you're not gonna get any chance to get the water. So you have to touch like that. Now you get some waters and fill the empty bucket, then you have to walk. And let me ask, what would be the best X in this problem? What do you think?
I think the best X is just under B.
Say that again.
I think the best X is just under B to
Under
minimize
B.
the time with the water.
Like this one. Okay, so let me, I guess the first thing that you guys can think, probably you get some meter effect, like here. Because the walking distance is, this one is same as this guy. So you guys can think probably this one is the optimal point, right? So here from A to this point is work with the empty buckets, and from this point to B work with the water filled buckets. And oh no. Let's do this one. So assume that this is D1 and D2, the distance. You can mathematically formulate these problems like that. And there is no constraint on X. X, the value can have any values. And you can use the CVXPY to ask to find the solutions, or you can use these geometric intuitions to get the meter point of B and get the straight lines to get the intersection is the optimal solution. But here, the difference between this one and that one is that you're gonna work with the empty buckets, and after you fill out the waters, you have to work with the water filled buckets, which is heavier. Right? So in that case, the distance problem, but you have to have different weights on it. It really depends on you. It really depends how strong you are. I want to penalize this one a lot, then probably like 2, or say you are extremely strong, so it doesn't matter you're gonna carry the empty buckets or water filled buckets. In that case, probably it's almost equals to 1. It really depends on your conditions or your situations. In that case, say it's like 1.5, then let me go back to, you have to multiply mu, which is the like tuning parameters. It could be like 2 or 1.5, or it could be 10. In that case, it's not easy to find the optimal solutions. Then you have to use CVXPY. Again, I'm going to skip all the things. I mean, you guys can figure it out. And let me see, this one is same as A minus X. The CVX dot ask to compute the norm, in the case 2 norms, not the first norm. And plus we have another, we have to compute another norms, in that here we have mu. I said probably in this case 1, probably next time you can change the value of mu's. Again, it depends on your conditions. And we have a constraint and to ask to CVXPY to compute to find out the optimal solutions. I mean, this is another example of that. I mean, this is the solutions. Another example is that supply chain problem management problems. Find out the minimum points that minimize the sum of transportation cost or distance from this point to 3 destination point. Say you have A, B, C as destination point. And you want to find out the locations in somewhere in the middle to find the traveling, minimize the traveling cost. All right. In that case, again, we can formulate it. And find out the solutions. And I'm not going to go in details, but probably think about this. And the difference here is that we can use two norms, or we can try in one norms or first norm to see whether you have the solution or not. Because I mentioned several times that definition of distance is not a unique. You can have different definition of distance or strength. It really depends on your interest. How do you define the traveling cost or transportation cost in this problem? And so far, I covered several problems to show you, actually to demonstrate how to use the CVXPY. And here, another example is that how we can program it or for the gradient descent method. And think about this problem. And if this is the objective functions without any, this is without constraint. Let me ask, what would be the optimal solution in this problem? X is x1, x of 2. We have two decision variables, no constraint, and it's a quadratic, so it's a convex problem. X of 1 and x of 2 can have any values. What's the optimal solution in that case? Actually, you don't have to compute it. Just looking at the objective functions, you guys can figure it out. Any ideas? It's minimization problems, but we have a squared. Always is going to be positive or 0. So when we can have zero as a minimum point. So optimal solution is, right? I mean, this is the too obvious. I intentionally picked these problems. Okay, let's see whether we can do iterative way. So whether the gradient descent method is gonna give us the same solutions, optimal solutions like that. And keep this one in your mind. And let me see here. I can this one. Let's try that one. Two squared. I can rearrange it. And here, and when I explain the quadratic functions, I use that definitions. But here is, I mean, it doesn't matter, but I had half in front of it. I mean, it doesn't matter. So in that case, I will say like that. Right? So this one what I got. And let me, so when you have this one as objective functions, and since I'm not going to use CVXPY here at this moment, I'm going to use a gradient. This is a method, and I have to compute the gradient. And for gradient of this guy over there, it's like that. And we have AX, H transpose X. But if you look at H, it's a symmetric. So it's a 2HX and it's HX. So that's why I had a one and half over there. And this one, let me see, that one is A transpose it is, so G transpose same as C. So this is the gradient that I can compute it out of this. And the gradient descent is the X, starting from X minus alpha gradient F. That's the definition of gradient descent. How do you update X? And let me here, what I want to show you guys, how do you program the gradient descent or this update rule in Python. So we define H and G over there. And this is a gradient F is H times X plus G. And this is the update rules in gradient descent, and repeat it. I mean, you can be 25 or 100, it's really up to you. And we have to set the value alpha step size. It's happened to be 0.2, it doesn't matter, it's probably, you can say 0.1 or 1. It's a tuning parameters. You have to try, you have to try with different values. And this is initial point of X. I said it's in how do you set the initial point? I think in general case, you have to set the random initial point. But here, what I did is I put, okay, this one is not, because this tells us the shape of X, so, and zeros. So actually, this is the initial point. It's starting from 0.0s, and that from that point, we do the updates. How many times? 25 times, hoping that it reach the local minimums. And in this case, it's convex problems, quadratic and convex problems, hoping that it's reach the global minimums. And it turns out almost, right? Remember that. So you can use the gradient descent. I just showed you guys how to program the gradient descent in Python.
Excuse me, I have a question.
Mm-hmm.
Why does the matrix H has to be a matrix of 2, 2? Can we just put 1 into the matrix and just remove the 1/2 in front of the?
Okay, I see. Let's. The question is that this is one way they can you can do this. Let's say I define. Let's define, suppose we have defined, forget about this, then gradient F should be, let me see, 2HX, right? In that case, then here, if you set this one in, remove that one, and 1, right?
Oh, okay, I see.
Then eventually I'm gonna have that one. But when you define over there, you're gonna have 2. So okay. It really depends on, I mean, depends on your preference. It doesn't matter.
Okay, thank you very much.
So let me see what I want you guys to try at home and change the number of iterations and see if, and change the number of alphas. Change the number of, change the value of initial point. I mean, this is like the easiest problems, so it doesn't see any big difference, but at least I want you guys to try with different, given this, and try different values to see if we can get different or similar result. All right, so that's the end of the optimization contents that I have.